So work from a non-constant force. We are going to represent a non-constant force two different ways. One is from a graph. Before we do that though, I want to go back to a graph type that we did quite a while ago. So if I gave you a velocity versus time graph, and let's put some numbers on it, 1, 2, 3, 0, 10, 20, 30, and we're gonna make it a nice, simple. As time goes on, the velocity increases steady, or linear function. So if I asked you from this graph to calculate the displacement, you would say, okay, displacement is velocity times time, but that doesn't work for this graph because that's only for a constant velocity. So I'm not going to do 30 times 3 to get 90. I know that instead I would use, the way we said it in first year, was the midpoint velocity. In this class, we talked about doing the area. So because we did velocity times time where the velocity is changing, we did the area. So this displacement, we'd have a triangle, so 1/2 times the base of 3 times the height of 30, so this would be 45 meters. But I could give you the same graph and I could extend ask you about acceleration. Well, acceleration is the rate of change of velocity. So this thing changed velocity from 0 to 30 in 3 seconds. So this is an acceleration of 10 meters per second squared. Notice we did rise over run. This was the slope. So in general, if your defining function tells you to divide to find the quantity you're interested in, you do the slope. If your defining function tells you to multiply, you do the area. So now if we have, sorry about that, a force versus position graph, so this is x in meters, 1, 2, 3, 4, 0, 100, 200, 300, force in newtons. So maybe I push something harder and harder, and then I slack off as it continues moving because I don't want it to get going too fast. So how much work did I do here? Well, again, I'm not going to say I pushed with a force of 300 newtons for the whole 4 meters because that's too much. Let's write down, remember work is the dot product of force and displacement. And so we would usually calculate that from FD cosine theta. Whenever you're asked a question about work from a non-constant force, you're either going to be given the force in the same direction as the displacement, possibly the opposite, or you're going to be told it's the component that's in that same direction. That would be like the F cosine theta part, so that you don't have to worry about the cosine theta. We'll use the shortcut work equals FD. And as I was just saying up here, the thing we want to calculate the work is a multiplication function. That means we want to do area. So area. I have 2 sections here. I was increasing my force and then I was decreasing my force. So the total work done in the first section, I have a triangle 1/2, a base of 1 meter times a height of 300 newtons, plus as I let up on the force, 1/2, again a triangle, times 3 meters times a height of 300. So this is half of 300 is 150, plus half of 900 is 450. So this is 600 joules of work. Some of you may not have noticed in previous times when we did this, you could have done this in one step. If you just want to know the grand total, this is a triangle. So 1/2 times the base of 4 times the height of 300, well, half of 4 is 2 times 300 is 600. You get the same answer. So the work done, you do the area. You would then continue the stuff we did before, that power is work divided by time, and that work changes energy. We've only talked about kinetic energy so far. However, I could, instead of giving you a graph showing you how the force changed, I could give you a function. So you also remember from when we did area, that turned into the calculus function of integration. So if you look on the College Board formula chart, you're not going to see this. What you are going to see is work is the integral of force with respect to displacement. So let's make a problem. A force is given by 12x to the fifth. Just totally making this f of x. I should write it this way. F of x equals 12x to the fifth. An object moves from the origin to x equals 2 meters. How much work is done? So because we have function notation, and we know we need to do the multiplication, force times distance, but multiplication is area, multiplication, that means it's integration. So our work is equal to the integral, and you put the number, your starting location, at the bottom, always. So from x equals 0 to x equals 2, the force function is 12x to the fifth dx. So the first step is just using your integration rule. In case you have forgotten, the integral of ax to the n, keep the coefficient, raise the power by 1, and divide by the new power. Now there should be a plus c, but we are going to do a definite integral with these numbers here, and I'll remind you how to do that here, but I'll write the plus c just because it hurts me not to. But that's the format. You keep the coefficient, you raise the power on the exponent, and you divide by the new power. So on this problem, we keep our coefficient, x to the fifth turns into x to the sixth, and divide by the new power, which is 6. We are going to evaluate that between 0 and 2. So first I'm going to simplify 12 divided by 6. So I have 2x to the sixth, 0 to 2. And then when I evaluate, I keep my coefficient, and then I plug in my numbers. So 2 to the sixth minus the whole thing again, evaluated at 0. So 2 to the sixth, I do not remember off the top of my head. It's 64. Then times the coefficient, 2 is 128, minus 0 to any power is 0, times anything is 0. So our final answer is 128 joules. Now, one thing I want you to notice about there is a little bit of direction stuff in here. This object moved from x equals 0 to x equals 2, so on a number line it would have moved to the right. Well, everywhere x is a positive number, these are all positive numbers, if x is a positive number, this force is a positive number, meaning the force is in the same direction. Okay? So because these are in the same direction, I got a positive number amount of work out of this. But this problem could have been given as, here's the force, let's have the object move from 2 to 0. You would work it the exact same way, but if you started at 2 and ended up at 0, you would have put 2 at the bottom and 0 at the top. It would just reversed here, and it would flip-flop these, and your answer would have been negative 128 joules. Because if the object moves the same distance in the same force field, but in the opposite direction, energy is not going to be given to it, it's going against the force, so it would lose energy. So that's how you deal with work from a non-constant force. You then put it back into work equals change in energy. And again, we've only talked about kinetic energy so far, but not too many problems next time.